So we left the last lecture on this slide. We were talking about the fractionation of carbon C13 and C12 by biological processes like photosynthesis. And I asked a question, if we are burning fossil fuel, which is old hydrocarbon, which was photosynthesized, which means it had less C13 compared to the current atmospheric composition. And if we keep burning that old carbon, does it show up as a carbon signature in the current atmosphere? Surely it does. If you look at the delta C13 from the corals that are growing now, so this is approximately over the industrial revolution period, and you can see that clearly as the fossil fuel combustion has gone up, C13 signature is being recorded by the coral, which is assimilating the CO2 from the atmosphere. And now the question is, if we burn so much carbon in the atmosphere, should it also show up as a reduced oxygen, because we use oxygen when we combust anything? And you can go and find graphs, the measurements are being made, and there is definitely a signature of a reduction in atmospheric oxygen because of so much additional combustion. Nothing to worry about, there is plenty of oxygen, so you are not going to run out of oxygen anytime soon. So we'll give one more example of a isotope and how it's used for reconstructing past climates, and this is now C14. So we talked about C12 and C13. What is C14? Tiny fraction of C14 exists in the atmosphere almost at a constant concentration, because it is generated by cosmic rays coming from the sun, which is bombarding the neutrons in the nitrogen atom that is there. And so it's converting, knocking off one of the protons from nitrogen, which has mass of 14, and it's replacing the proton with neutrons. So when you remove one proton from nitrogen, it goes from 7 to 6. So it's not a nitrogen anymore, because it's a carbon. Carbon has 6 protons. So the nitrogen 14 has been converted to C14 by replacing one of the protons with a neutron because of this cosmic ray bombardment. So since the cosmic rays are always bombarding the atmosphere, there is and there is a lot of nitrogen in the atmosphere, the major constituent, lots of C14 being generated. Well, a constant amount of C14 is being generated. Of course, when cosmic rays change, there is a slight change which has to be tracked as well. So that C14 is unstable, and when photosynthesis happens, that C14 along with C13 and C12 is being assimilated into biogenic material. So as long as the trees are alive and photosynthesis is going on, the organic matter has similar C14 amounts. It's not necessarily the same as the atmospheric concentration, but in its lifetime it has a similar concentration, except if the organic matter gets buried and it's not photosynthesizing anymore, like in the sediment in the ocean, or a tree that dies and gets buried, or the hydrocarbon in like the fossil fuels, old hydrocarbon, that C14 begins to decay. So as we saw in the table before, C14 can be used for dating up to about 50,000 years. So material that's decaying over this period can be done by looking at the reduced amount of C14 in this old organic carbon compared to the present C14 that exists, assuming that similar amounts existed when it was photosynthesized into this organic matter you are looking at. How does this become useful? So you have to now combine your thermohaline circulation, where we said heavy water is being formed in a few spots like the Greenland, Iceland, Norwegian Sea in the North Atlantic and the Southern Ocean. So that water, I said, is taking everything with it. So it's taking certain amount of C14 that's there in the atmosphere with it, and once it gets away from the surface and sinks into the ocean, that C14 begins to decay. So if you take water samples from different parts of the world ocean, for example from the North Pacific compared to, let's say, North Atlantic, you expect that the water that's sinking in the North Atlantic is much newer. It has just formed and it's sinking, and that water is inundating southward into the Southern Ocean. And as we said, it's combining with the water that's forming also in the Southern Ocean, and it's circulating, and deep water is coming into the Indian and Pacific Oceans. And we said that time scale is 100 to 1500 years. And you can see that as you go away from the regions where atmospheric C14 is new, the depletion of the C14 increases because it's getting older and older. So the circulation age can be inferred that way. So the water in the North Pacific is almost 1200 years or older. The Indian Ocean is a little bit fresher because it's much faster than the Pacific. It's much smaller, a little bit shallower, and so on and so forth. So you can see how beautifully unstable isotope like C14 gives you a map of the age of the water at the bottom of the ocean. This is how isotopes are used in all these circumstances. Glaciation also leaves physical signatures. So you could be sitting somewhere in the middle of Deccan Plateau and have signatures of past climates. So these are here, the markings are called glacial striations. So as ice grows, it keeps scratching everything, right? And it carves holes because the water seeps in and freezes and expands. So you can see that the rocks have been carved by the ice that grows. So this region, it may not be currently in the glacier region, it may be glaciated in the past. It will have the signature from the glaciers. Other evidences of glaciers come from things like this. These are called moraines, or the material that is ground up by the glaciation. So any material, rocks buried in the soil or the rock itself, etc., get kind of either made into pieces and pushed along. As the glacier grows, it keeps pushing it along. So you get sometimes what is called a terminal moraine, which means the glacier extended up to that extent before retreating because of climate change. So one of the most striking examples of a terminal moraine is a long island called Long Island off of New York City. During the last ice age that ended about 20,000 years ago, the glacier came all the way down to New York, and it left this terminal moraine, which now has become an island that is inhabited by human beings. The other things you typically look for are things that are kind of out of place. So these are these boulders that are suddenly sitting in the middle of nowhere. Where did they come from? So the glacier rafted debris, for example, you can go in the middle of the Atlantic Ocean and find these huge boulders that don't belong there, basically because they were transported there by the glaciers along. For example, the glaciers in the Himalayas are very famous for being full of debris. So when the glacier moves, as I said, glacier is like a molasses. It can move, it flows. And when it flows, it carries stuff that's frozen into it. There are examples from the 1920s, for example, when a famous oceanographer called Nansen tried to go to the North Pole and his ship got stuck. And the ship got drifted by the ice for some time before it got crushed. So next time he went, he had reinforced his boat to survive such crushing by the ice. So ice can crush things and it can move things, and you can find these evidences in different places. So these are morphological or physical evidences. The other thing glacier does is create what are called tillites. So it grounds up things and mixes them together, different kinds of rocks, different combinations of rocks that have been ground up and reformed. So the smaller rocks have been buried into bigger rocks during the glaciation and the glacier flow period. So glacial striations, moraines and terminal moraines and tillites are typically physical evidences of glaciation. Just to kind of summarize some of these things, what are the time scales at which these paleoproxies become useful? So we have instrumental records going back to about 100 to 200 years, and historical records go a little bit further, and there are sometimes older records emerging from the pyramids or the archaeological sites in various countries in Africa or India or China and so on and so forth. The tree rings give us evidences going back to about 10,000 years or shorter. Trees can live for many thousand years. There are biological details as to why that happens. Very briefly, when the DNA replicate as we grow older, our DNA's chromosomes tend to lose a little bit of the edge, and that's how we age, whereas trees clone their DNA or the chromosomes perfectly so they can live much longer. So we get very long records. And ice cores, they can give, as we saw, hundreds of thousands of years. Lake sediments, again, depends on how long the lake has been around, whether it's been perturbed by human activity and so on. And sometimes the lake may have disappeared, but you may have old buried sediments there anyways. So you can extend the time scale to millions of years. Coral reefs, also in hundreds of thousands of years. Ocean sediments, as we said, the ocean floor has reformed over the last 200 million years, so we hardly get anything beyond about 200 million years. Continental coastal sediments can have signatures that are much longer. They may be sedimentary rocks, for example. So the sediments have metamorphized under pressure and temperature into rocks, and sometimes the sea level changed or the continent rose. So you can get sedimentary rocks high up in the mountains, like in Colorado or Ohio and so on. So there are many places where sea level has changed or the continent has moved, and the sediment that was originally underwater in the ocean can get exposed, but it has past climate information. So if you date it and then look at the chemical signatures, you can say what the climate was like in that period. So those are kind of the summary of some of the paleoproxies. We didn't cover all of them, but we covered majority of the most important ones that are most often used to reconstruct past climates. So you can read up more and more. There are many chemical processes involved, there are many isotopes involved. We didn't cover all of them here. So let's conclude this section of data, archives and models by briefly looking at models. As I said, the most useful application of models, numerical models or computer models, is to project climate into the future. If we want to know how temperature will change, how precipitation will change, how vegetation will change, etc. into the future, we end up making some assumptions of how population will grow, how technology will change, how energy usage will change, how people will move around, etc. and put that along with a fluid dynamics model. What is a fluid dynamics model? Essentially, that's going to represent the Earth that we live on as a number of boxes, or called grid boxes. So you can see here there is a box of a certain size. It's like a cube. So the entire sphere will be covered with a cube or hexagons or tetrahedrons. Different numerical models use different kind of grid structure, but essentially they solve equations of fluid motion like F equals ma, Newton's law of motion, and it solves thermodynamic equations so that you can track evaporation of water, condensation of water, formation of clouds, movement of clouds, precipitation formation, and so on and so forth. So the weather forecasts you see and the climate forecasts you see are using such fluid dynamic models. So the similar models will be used sometimes to simulate past climates. If we know how the radiation was working at that time, how the continents were arranged, we can simulate past climates so that the incomplete information we have from paleoproxies can be completed by simulating past climate variability from these numerical models. Okay? So there are various details. Each grid box will carry winds, temperatures, humidity, chemicals like carbon dioxide, dust, water vapor, etc. And it takes incoming solar radiation that we discussed and compute the outgoing long wave radiation. Everything is done within the model. So the model knows where there is cement, there is a different albedo, where there is vegetation, there is a different albedo, where there is an ocean, there is a different albedo, and it changes with the sun's angle. The length of day changes with latitude, and the land configuration is changing all over the place. Heat capacities are different. It knows all these things. So you just give it information about incoming solar radiation. It does lots of calculations, trillions of calculations on a computer, on a supercomputer, and then spits out all the details of when it's going to rain, where, how fast the winds are going to move, etc. And depending on the model, it can also generate hurricanes, it can be used to predict hurricanes, and so on and so forth. So not one single model is going to do everything. Sometimes we only run an ocean model, sometimes we run only an atmosphere model. So if the ocean model is running, you will put winds on top, you will put the heat flux on top, and so on. If only the atmosphere model is running, you will put radiation and you will prescribe the surface temperatures or something like that. So all sorts of details are there. So the land model or the ocean circulation model has also similar grid structure. It's a bit more complicated because the coastlines are uneven and jagged. So you need to create grid boxes to cover these kind of uneven distribution, and it's interacting with the atmosphere. So when the atmosphere warms up, the ocean feels it, it evaporates more, it gives it water vapor, and when the winds blow, it's being dragged. When it hits the continent, it turns depending on various other dynamics that we haven't gotten into, and it has the vertical structure of the ocean, and all these are solved together. So these things called air-sea interactions are important because they both talk to each other. The heat capacities are different, but the ocean is constantly being forced by the atmosphere. That's the big difference between the atmosphere and the ocean, right? The atmosphere is basically allowing almost all of the radiation to go through, heat everything, and it's being forced from the bottom. Whereas the ocean, the bottom forcing is very small. There may be some geothermal heating, some little hydrothermal vents which are very negligible, but it's mostly being forced from the top by momentum from the winds, the heat, and exchange of water vapor through evaporation, and so on and so forth. So these models are pretty amazing now, but they have taken many decades to come along. When things started, when the computers got invented and people started to put together models in the mid-1960s, simple atmosphere and land surface models were first designed. They started to run, and given the radiation, they started to produce very realistic solutions, and you can imagine how amazing the time was when for the first time people were able to simulate global circulations. Preliminary weather forecasts started being made. Mostly happened in the United States of America, places like National Center for Atmospheric Research and Geophysical Fluid Dynamics Laboratory, and so on. The same place also developed an first ocean model, and in the 70s and 80s they also added details like vegetation to it and some sea ice to it. The thermodynamics of the sea ice is very interesting and very complicated. So all that has lots of impacts on the circulation, air-sea interactions, and so on. And in the 90s, the sophistication of the models began to increase. We began to realize that all the coal we are burning and the fossil fuels we are burning are producing so-called aerosols, lots of aerosols, pollution that then aggregates with humidity and so on, especially sulfate aerosols, which is a byproduct of coal burning, because it's very reflective. In fact, it can cool the climate, but it can produce things like acid rain. That was added, and it turns out that it also affects cloud formation. So if you have more dust particles, they act as so-called cloud condensation nuclei. When you have water vapor to form clouds, you need these nuclei around which water can condense, and they can aggregate and collide and get bigger and form a cloud. So aerosols have a huge impact on the clouds, plus they also have an impact on the rain. If you have lots of cloud condensation nuclei, then you will get drizzle instead of heavy rain. So the so-called microphysics of the cloud itself changes when you have lots of dust. And we also began to add so-called solar forcing, which means the variability in the sun's output because of sunspots, etc., and volcanic forcing or volcanic aerosols, because when volcanoes go off, they spew lots of ash and dust in addition to carbon dioxide and methane and water vapor and so on. So, in the present day, we are moving towards what are called Earth system models. So, we have added carbon cycle both in the atmosphere and the ocean. There are so-called dynamic vegetation models, and they are doing much more details of the aerosols, including sea spray, mineral aerosols, and so on. So, you can imagine now the feedbacks in this are going to be very complicated. Dynamic vegetation will allow you to look at how a forest cover affects the local microclimate, local clouds, local humidity, and the albedo, and how it will affect the warming and cooling with carbon forcing, how carbon forcing will affect vegetation. For example, if the leaves have something like stomatas in the leaves, the stomatas open basically to gather CO2, but they have to stay open just long enough so that the water that has been brought up from the roots doesn't get lost. So, there is something called stomatal conductance, which is optimized for the CO2 level. If you increase the carbon dioxide, then they don't need to remain open for too long because there is more CO2 in the atmosphere. So, they close rapidly, which means the water they had brought up is excess, and that water will be released back. So, there is some evidence that plants are now releasing more water because of increased CO2. So, there are all these sorts of carbon fertilization effects and so on. Plus, we are now also having crop models and so on, which tell us how these so-called C3 and C4 plants will respond. Remember, we just learned about briefly C3, C4 plants, which respond differently to changes in temperature and carbon dioxide. So, who will respond better, who will suffer, which species will survive, which species will not survive, and so on. So, by now, these models have all sorts of components all together, including ice sheets, so glaciers, so-called biogeochemical cycles, which means they are doing carbon monoxide, ozone, methane, and all the other details. And they also are beginning to add human beings as part of the so-called Earth system. When people move, what happens to the climate? When people cut forests, what happens when they do irrigation or clear a forest for agriculture? What happens to climate? All these sorts of things are now being captured by these models. So, the models are essentially going towards what we would call the physical climate system where we started, but adding biogeochemical cycles and all the feedbacks in between, including the external forcing from the sun and the volcanoes, but also the external forcing because of human activities. So, you can do climate change and climate variability. These are now called Earth system models. They are actually much more complicated. These are just a simplified depiction of the main processes. Okay, so you can see that the global moisture sits here in the middle, for example. We said that's a very critical component of the climate system. So, when we started the so-called IPCC or Intergovernmental Panel on Climate Change under UNFCCC or the United Nations Framework Convention on Climate Change, I think you have all heard of IPCC, which puts out this big report every few years about the past climate variability, what changes have occurred, and projections of future climate, what changes will occur. And we have improved the models. The grid sizes used to be about 500 kilometers on a side, which should give you pause, because that means in the 1980s and early 1990s when we started, computer power was not enough. So, the sphere was converted into grids by very few grids to keep the computation cost minimum. So, 500 kilometer grid means a cloud would often be 500 kilometers large. Are there 500 kilometer clouds? Of course there are. When monsoon happens, it's very large, but it rains only on spotty places. So, all those kind of processes are the representation of the Himalayas or the representation of the coastlines was not done as accurately as we would like. This is called the first assessment report, which came I think in 1991, second assessment report, third assessment report, assessment report 4, we have had assessment report 5 that came out in 2014, assessment report 6 will come out in 2021, and you can see that the resolution of the models, and you can see the feature, the mountain here is hardly visible, becomes more visible here, and it has become much more realistic by the time you get to 110 kilometers. So in addition to improving the processes from soil to vegetation and ocean biogeochemistry, the ocean nutrients, phytoplankton, zooplankton, etc., how much carbon is going where and so on, the representation of the features, physical features themselves has improved, because if the Western Ghats are not done properly, you are not going to do the rain properly on the coastline of India, and you will not do the rain properly in the interior India either. So improving these kind of features, Himalayas, Western Ghats, etc., obviously gives us much better representation of climate at all time scales. So here is details of some of the processes, including atmosphere, land, ocean, ice, and biosphere, which is the vegetation, sometimes includes details of the crops, ocean including marine biology, fish, because you want to have the full carbon cycle, and you want to be able to say in the future what will happen to marine resources, where will you grow food, where will some crops not grow anymore. If temperatures get very warm, for example, even if rainfall increases, some crops will not grow because the photosynthesis gets saturated at some temperature, and so on. So all these models can tell you, and you will get what are called emergent solutions, things that you didn't even expect. For example, when you have a agricultural model coupled to atmosphere, ocean, and the coastal ocean, etc., you will use the model to say what is the optimal crop pattern for improving the soil quality. So soybean and corn and wheat and so on, each one has a different soil leaching property, fertilizer use, water withdrawal, and so on. And then you run the model and you track the nutrient flow into the waters, and it turns out that what is good for the soil quality is not necessarily good for the water quality, because the water gets polluted with more nutrients, you will have more algal blooms and then more harmful algal blooms and so on. So we need to use such models to look for the solutions that are not obvious just by doing simple calculations. So you have all kinds of interactions of vegetation and animals, rivers, snow melt, glacier growth, and how the pollution is affecting the ozone, the clouds, cloud distribution, etc., etc., etc. So we will finish this lecture with a few take-home points. So Earth's geology and biology leave lots of chemical signatures. In fact, in the 1920s, Vladimir Vernadsky had created something called geobiology and biosphere and so on. These were new terms at the time, but he was convinced that biology is leaving geological signatures. And this turned out to be true, that biology through sedimentation and impacts on water pollution and chemical loading, chemical weathering, for example, rocks, when they have moss growing on it and they set roots, they enhance the rate of weathering. And why is weathering important? Basically, weathering is water in the atmosphere is taking CO2 and producing carbonic acid, and that carbonic acid is leaching the rock and producing calcium carbonate and so on that is flowing into the ocean. This is a very important process of removing carbon dioxide from the atmosphere. So chemical weathering or biologically enhanced chemical weathering is an important process on long time scales, on geologic time scales. So those kind of processes and the faster human activities and so on are all leaving signatures. For example, the coral delta C13 is a human signature that's producing a chemical signature in corals, right? So the chemical reactions record climate variability and change. So corals, as I said, have striations or layers that can be as finely resolved as a week. So if you have few years of coral data, you can look at the data and can infer monsoon variability over the Holocene, El Nino variability over the Holocene. We haven't defined what El Nino is. We will do that later, but I'm sure some of you have already heard about it. So it's not just trends or climate change over hundreds and thousands of years, but even the ups and downs of things like the monsoon that can be found via these biogeochemical signatures. So this is a very key phrase, biogeochemical, because biology is involved and geochemistry is involved to produce these proxies for climate variability and change. Models solve equations of motion and thermodynamics and energy to compute climate variables, and they compute everything, as I said, temperature, humidity, winds, they give you clouds, rain, vegetation. We also have crop models, ocean circulation, ocean biological production, zooplankton to fish. Some models are sophisticated enough to do turtles. I myself have been involved in a model that is now being used for turtles. So you need some knowledge of biological information like their growth rates, their spawning habits, their habitats, their thermal conductivity, etc., etc. So the process understanding that exists about any biological, chemical, and physical systems is converted into a numerical system and solved as an earth system. So this earth system concept is something that's very important because everything is interlinked, as we will see with some examples of feedbacks. Weather and climate predictions are now routine. Every morning, many centers in the world, including the National Center for Medium Range Weather Forecast in Delhi and the India Meteorology Department in Pune, every morning from the computer they produce forecasts of several days to several months. And we didn't go into the details, but actually weather forecast is done for a few days and the system becomes chaotic after a few days because of the dependence on where you started, but still you can make climate predictions. So in May, IMD will say this monsoon will be normal or not normal, for example. How is it that they cannot say if it will rain or not on June 5th, but can still say monsoon will be normal? There are some details, but essentially it comes down to, again, the memory or the heat content of the ocean. The heat content of the ocean is so large that the sea surface temperatures change slowly and they control the atmospheric behavior. So over a few days, the atmosphere can move fast because it has low heat content and the ocean doesn't care. Okay, you do whatever you want. But if it tries to dance too many days, then the ocean says, wait a minute, you cannot do whatever you want because I will control you. So this is called predictability of the second kind, but you don't need to worry about the details. So essentially, weather prediction, especially in the tropics, can be only a few days, but for climate prediction can be few months to sometimes even a year and so on, depending on what process is involved. Future projections, we didn't say very much in terms of how exactly the projections are made, other than that I said there are assumptions of population growth, technology change, energy production change, etc. But in the end of this series of lectures, end of this course, we will have several lectures focused just on how the projections are made, what the projections are saying, what may be the uncertainties in these projections, and how do we interpret these projections, and how can they be used for making future decisions like mitigating the change, climate change because of our action, or adapting to the change that's happening or will happen. So we'll look at those in more detail at the end of this series, of this course. For now, just remember that the same models that are used to simulate past climates, present climate is being used to project into the future with some assumptions, because for the past climate and present climate, we know almost everything we need. For the future climate, we don't know many of the things of how vegetation will respond or how sea level would have changed. All those have to be computed, and some of the things have to be separately computed like population growth. Some of the things have to be prescribed in a certain way as to how much carbon dioxide will continue to emit. But more importantly, they will allow us to say, if we need to reduce carbon emissions, what are the pathways? And if we follow these pathways, what will climate change do? So how to minimize climate change, how to minimize the impacts of climate change. That's kind of where we will go in the coming lectures. So these are the main take-home points from climate data, climate archives, and climate modeling. See you next time.